So, welcome again to another introductory astronomy lesson, courtesy of Bella and me, Jamie Lombardi. Today's lecture is going to be for Monday, March 30th. I chose an astronomy picture of the day from 20 years ago, actually, because it had this beautiful picture of the globular cluster M4 zoomed in on it, and what the circled stars are, they are white dwarfs. And we were learning about white dwarfs last time, and we'll be learning more about white dwarfs today. So, without further ado, let's get into it. We're now into chapter 14, and we're going to be learning about the stellar graveyard. That is, what happens when stars die. And there's going to be three kinds of compact objects that are made: white dwarfs, neutron stars, and black holes. And we'll be talking a little bit about all three of those today, starting with white dwarfs. We said last time that these white dwarfs are objects that are left behind when low-mass stars and intermediate mass stars die and make planetary nebulae. And the core of that star is then a white dwarf. The outer layers of the star are what become the planetary nebula. And so just like the core of the star that formed it, a white dwarf is supported by electron degeneracy pressure. And it's not hot enough for there to be fusion any longer. So it's not a star in the sense that it is currently converting mass into energy. There's no ongoing fusion inside of it. But it's a star by virtue of the fact that it used to be doing that. The perhaps most famous example of a white dwarf is Sirius B. Sirius is that brightest star in the night sky that you know about. It's in the Big Dog Canis Major constellation. It's actually a binary system, and through a telescope you can, if it's a good enough telescope, see the two individual stars. Sirius A is the bright component. That's the component you could see just with your naked eye. Sirius B is the dimmer component, and that's the white dwarf. So, as a reminder, we talked about how low-mass stars like the Sun evolved last time. They're on the main sequence, subgiant, giant, helium flash, helium burning, asymptotic giant branch, and then they eject their outer layers to make the planetary nebula. The core is then revealed. It's nice and dim and also very hot, and then it cools off as it radiates away energy, getting dimmer and dimmer all the while. So white dwarfs are typically the mass of the Sun-ish. So for example, Sirius B is very nearly, as it turns out, about the mass of the Sun. However, they are the size of the Earth, not the Sun. And remember, you can fit 109 Earths across the width of the Sun. And so these white dwarfs are much more compact than the Sun is compact. Now, the way that white dwarfs work is that as they get more and more massive, they actually get smaller. Remember, we've talked in the past about how when you stack pillows on top of one another, at some point, if you add an additional pillow, it'll actually get the stack of pillows to become smaller because it compresses everything beneath it enough that the stack becomes smaller. And you can think of the same thing going on here with white dwarfs. As you pack more and more mass on it, the equilibrium structure is actually that of a smaller and smaller white dwarf. And so imagine you had a 1 solar mass white dwarf and you could add matter to it. It's 1.1, it's smaller. 1.2 solar mass is smaller still. 1.3 solar mass is smaller still. And you may reasonably ask, is there a limit to this? And the answer is yes, as first realized by Chandrasekhar. White dwarfs cannot get any more massive than 1.4 solar masses. What happens is, as you try to add more and more mass on it, it gets smaller and smaller and smaller in size. And you can't get anything smaller than 0. More specifically, what will happen to the electrons as you make the white dwarf smaller and smaller is that they move around faster and faster because of that exclusion principle that we talked about before, the thing responsible for the electron degeneracy pressure, that fermions don't like to be in the same state as one another. So if you start packing them really, really close together to be in a different quote-unquote state, they need to be moving much more quickly. But nothing can move faster than the speed of light. And so if these electrons are not able to move any faster, something new is going to happen. You're not going to be able to have an equilibrium structure. That happens right around 1.4 solar masses. That's the Chandrasekhar mass limit, or the white dwarf limit. So, okay, fine, that's interesting that there's this upper limit. Let's start to talk about a scenario where you might approach that limit. Imagine that you have two stars in a binary, and one of them is a white dwarf, and the other star is, say, a giant star that's going up the giant stage, so it's getting bigger and bigger and bigger. At some point, it's going to be big enough that the matter will stream off of its surface down around the white dwarf. So here's the white dwarf at the center of this accretion disk. Here's its binary companion, and the matter from that companion is streaming down and around the white dwarf to form that accretion disk. Now, because of friction between the matter as it orbits in that disk can get very hot, it can glow. It's best to look for that in the X-ray, because this will be very energetic light that is emitted from such a warm, hot region. And so what can happen to the white dwarf is what's called a nova. That the matter from that accretion disk, because of the friction, it'll gradually spiral in, and it can be accreted onto the surface of that white dwarf, and it builds up there and gets denser and denser and denser, and it can get hot enough for fusion to begin on the surface of that white dwarf, and you can have an explosive event called a nova, where fusion occurs in a shell on the surface. For a few weeks, the star can brighten up to 100,000 times as bright as the sun. And then it settles back down to what it was like before. The white dwarf is left intact after a nova like this. Nova refers to new. And you could imagine perhaps that this gets bright enough to make a new star in the sky, so to speak. These kinds of explosions are called novae. The plural is N-O-V-A-E. The singular is N-O-V-A. So, take-home message, you can be building up the mass on the white dwarf, but it doesn't destroy, this nova does not destroy the white dwarf. We'll get to that in a moment. What happens to a white dwarf when it accretes enough matter to reach the Chandrasekhar mass limit of 1.4 solar masses? And so A, it explodes. B, it collapses into a neutron star. C, it gradually begins fusing carbon in its core. Okay, pause it if you need to. All right, well, we'll talk about neutron stars soon. And indeed, neutron stars will typically have around a mass of 1.4 solar masses, but that's not what's going to happen here just yet. Instead, what happens if you try to exceed that Chandrasekhar mass limit, the star will start to collapse in on itself and heat up in the process, and you'll have a runaway fusion event that'll just blow the star to smithereens. These are called white dwarf supernovae, or type 1a supernovae. And so we've now mentioned two kinds of explosions, novae and supernovae. They're both energetic, but supernovae are much, much more energetic and much, much more luminous. In fact, they can be 10 million times as luminous as a typical nova. And so in the nova, remember, the white dwarf star is left intact. And in fact, white dwarfs can go through nova events repeatedly. In a supernova, the star is blown apart. And so that'll only happen once at the end of that star's life to generate a supernova remnant. Now, you'll remember last time when we were talking about the evolution of high mass stars, we talked about massive star supernovae. And now we're talking about white dwarf supernovae. So there are two distinct types of supernovae. In both cases, the star is blown apart. In the case of the type 2 supernovae, you leave behind a black hole, or I'm sorry, the massive star supernovae, you leave behind a black hole or a neutron star. And that massive star supernova is triggered when an iron core collapses in on itself and then rebounds and explodes. The white dwarf supernovae all occur in the same way, really. You've got a white dwarf in a binary. It's accreting matter from a companion, and the mass of that white dwarf creeps up on the 1.4 solar mass limit, causing it to explode. And so massive star supernovae, they can have a range in their initial conditions. Not all stars are going to have the same mass before they go through a massive star supernova. White dwarf supernovae, they all occur pretty much the same way, right? Where you have a 1.4 solar mass white dwarf blowing up. So there are a couple different ways observationally that you can distinguish between white dwarf and massive star supernovae. One is with their light curves, right? They will have distinct characteristics in their particular light curves. So in a massive star supernova, it gets brighter over a time scale of a month or two and then starts to dim off. This is the luminosity on the vertical axis here and time on the horizontal axis. And so here it has this shoulder. It's kind of almost a plateau, if you will, where it holds roughly the same luminosity for a month or two before it starts to then dim more quickly again. And the white dwarf supernovae light curves, they go up and they come down and they have a different shape. So by looking at the shape of this light curve, you can tell which type of supernovae you're dealing with. Notice one thing here as well. This peaks out the white dwarf supernova at 10 to the 10 or 10 billion times a solar luminosity. That means that this gets as bright as 10 billion suns at its peak brightness. Another thing to note is that since all white dwarf supernovae happen the same way, that 10 to the 10 number is pretty much the same from case to case. I mean, yes, it's true. There are astronomers that spend their careers worrying about the details of whether or not you have exactly the same case from case to case. It could be that different compositions of the star that you have beforehand are going to give you different light curves, and certainly that is the case and does happen. But to a good approximation, all the white dwarf supernovae are going to peak at 10 billion solar luminosities. The peak massive star luminosity is going to change a bit from case to case. Another difference between these two supernovae that you can look for observationally is that white dwarf supernovae won't have any hydrogen absorption lines. If you think about how they occurred, you've got, say, a carbon, maybe an oxygen white dwarf, not really hydrogen in it. Yes, it's accreting some hydrogen from the companion star that puts it over the limit, but the vast majority of mass that's participating in the supernova explosion is not hydrogen. So when that white dwarf blows up, you don't see any hydrogen lines. As opposed to a massive star supernova, remember how that occurs. You've got an iron core that implodes and rebounds and blows off the outer layers. Those outer layers are largely made of hydrogen and helium. And so in massive star supernovae, for most cases, unless that envelope had been stripped, you're going to have hydrogen absorption lines in the spectrum. So there are other ways besides just the profile of the light curve that you can distinguish between these two types. Okay, so neutron stars are our next compact object. White dwarfs, they're very compact. Remember, mass of the sun in about the size of the Earth. Neutron stars will turn out to be even more compact than that. And so when you have a massive star supernova, then what will happen, remember, is that it's triggered when the electrons in the core, which were supplying the electron degeneracy pressure supporting the core, merge with protons in the core to make neutrons and neutrinos. And that removes the degeneracy pressure, replaces the electron degeneracy pressure with the far weaker neutron degeneracy pressure. And you don't have electrons anymore. And so what do you have? You've got a lot of neutrons in that core there. Those neutrons do have some pressure, given by neutron degeneracy pressure, but what happens is that core will be able to maintain an equilibrium shape which is smaller than before. And then the outer layers get blown off in a supernova remnant. What's left behind is a neutron ball. That is the neutron star. Here down in the lower left, we have an X-ray image of the neutrons of a neutron star and its surrounding supernova remnant. So neutron stars, like I said, are smaller than white dwarfs. How much smaller? They're typically the size of a small city. Maybe around 10 kilometers, 6 miles in radius. Here you can see a map of the greater Meadville metropolis area. And this grayed out region is showing you about how big a typical neutron star would be. Neutron stars were discovered by Jocelyn Bell back in 1967. What happened was that she was one of the first people to be using a new radio telescope, and she was looking out in the sky, and she realized that when she pointed to a particular place in the sky, she would see a regular pattern of radio waves. They would be bright and then dim for a second, and then bright again, and dim for a second, and bright again, and then dim, etc., etc., etc. And at that time, there was no known natural source for such a signal. In fact, on the original readout, she wrote the letters LGM, which if you carefully did the reading, you will know stood for Little Green Men with a question mark at the end. And we know now that we weren't being contacted by LGMs, but if you think about it, if you put yourself in her shoes, it's a very reasonable thing to wonder. I mean, to look up in the sky and see this regular pulse coming your way, and not have any natural explanation for what it may be from, what else might you think? You might wonder, hey, I'm a graduate student. Am I the first human to ever be contacted by an extraterrestrial species? I actually found a little YouTube clip that I wanted to show you that will play here that has Jocelyn Bell talk about that discovery. She found the first neutron star, and then I'll let her describe what happens here next.
That bit of the sky due to go through the telescope beam at 2 o'clock, 3 o'clock in the morning, December the 21st, perishing cold.
Here she's looking at a new point in the sky.
Switched on the high-speed recorder and it came blip, 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 blip. Clearly the same family, the same sort of stuff. And that was great. That was really sweet. It finally scotched the little green men hypothesis, because it's highly unlikely there's two lots of little green men, opposite sides of the universe, both deciding to signal to a rather inconspicuous planet Earth at the same time, using a daft technique and a rather commonplace frequency. It has to be some new kind of star, not seen before. And that then cleared the way for us publishing, going public. Martin Ryle called up the editor of Nature, John Maddox, and more or less said, we've got something interesting coming. Didn't quite say hold the presses, but he nearly did.
Now, the people here say that if they got 3 signals as exactly spaced as that, it would be very unusual. If they got 4, it would be phenomenal. Well, they've had pulses as exactly spaced as that 24 hours of the day since November.
Well, these signals that we're picking up are entirely new. Nothing like this has been seen in radio astronomy before.
The excitement was because this was a totally unexpected, totally new kind of object, behaving in a way that astronomers had never expected, never dreamt of.
So what she was finding here was the first pulses from so-called pulsars, and we'll talk a little bit about the mechanism that causes these pulses in just a moment. But I guess I'm actually embarrassed to say, I'm embarrassed for the sake of humanity to say that her advisor ends up winning for this discovery the Nobel Prize, and she was left out of the mix, to the enragement really of many in the community. My advisor, when I was in college, he wrote the book on pulsars. In fact, I mean, literally, he has a book titled Pulsars, and he dedicates this book to Jocelyn Bell. Of course, I'd rather have a Nobel Prize awarded to me than a book that had been dedicated to me. But nevertheless, she has become well known for being the discoverer of pulsars under work that she was doing while in graduate school. So we say here that these pulsars are from spinning neutron stars. For example, the Crab Nebula, the supernova remnant that we mentioned earlier before, at the very center of it, there is a pulsar. And so here down in this inset rectangle, this is representing those pulses. The horizontal axis is the time axis, and the vertical axis is a slit across the center of this particular region. And so what's going on here is that we have a bright pulse of radio waves, and then there seems to be a secondary pulse, and then a bright pulse, a bright pulse, a bright pulse, at a rate of about 30 times per second. Every 0.033 seconds, you get one of these bright pulses. The vicinities of these pulsars are very dynamic and energetic. Let me play you some imagery data. The images on the left were taken by the Chandra X-ray telescope, those on the right by the Hubble Space Telescope, when it was visualizing or observing rather in the visible light. And what you can see here is that there are pulsations that are occurring, there's material that is orbiting, there are actually jets which come out from the pulsar. So here you can see the pulsar center right there. The jets that I'm talking about are coming out this way in the direction perpendicular to all of the rings. To give you an idea of length scale, this inner ring is about 1 light year across. So the mechanism here has to do with the fact that these neutron stars are spinning. They're spinning very fast indeed. They'll spin around on their axes tens or hundreds of times per second, typically. And as they do, they have a beam of radio waves which is coming out. This beam is generated by moving quickly charged particles. And that beam sweeps around, not unlike the beam of a lighthouse and how that would sweep around over time. And so here in this image, this vertical axis is the rotation axis. The star, the neutron star, is spinning around that axis, and the beam is off axis from the rotation axis, and so that sweeps a cone through space. If you are in that cone, you the observer on Earth, Earth itself, then you will see as the beam sweeps by a bright blip of radio waves, and then the next sweep around you'll see another blip as well. So here's a thought question for you, yes or no. Could there be neutron stars that appear as pulsars to us? Oh, I'm sorry, let's say that again. Could there be neutron stars that appear as pulsars to other civilizations, but not to us? Go ahead and pause it if you like. And the answer is yes, right? Because if you think about this, imagine Bella is one observer and I'm another observer. And if the beam happens to be sweeping around and it sweeps past Bella's eyes, then she on that other planet in some other star system would see a pulse. However, the beam is never sweeping past my eye. And so me on planet Earth, I never get to see that neutron star as a pulsar. Or it could have been the other way around, of course. Maybe the beam sweeps by planet Earth, but not the extraterrestrials, and then we would, on Earth, see it as a pulsar, and they, on the other planet, would not. So here's that lighthouse analogy that I was talking about. Just as a lighthouse will send out a beam of light over the ocean that rotates around, and then if you're on a ship, you'll see it flashing if that beam passes by. Here, you can imagine looking at a neutron star in space, and if that beam sweeps by the direction you're looking, you'll see the radio wave intensity increase there. If you look closely, this is animated right there. There's a little red dot that's tracing out the intensity of the radio waves. And so it's low whenever the beam is not pointed in our direction, and when the beam happens to be pointing by us, then it would get bright for that moment. Now, neutron stars, I said, are as big as a city and spinning around tens or hundreds of times per second. So they are moving really quickly. Why is it that they're moving so quickly? It's from conservation of angular momentum. When that core of the star that's going supernova collapses in on itself, it'll start to spin faster and faster and faster. Remember earlier in the year, I did a demonstration where I was on a rotating platform and I pulled in my arms while I was holding on to some weights, and I spun faster and faster and faster. Remember, angular momentum is, if you will, mass times sideways velocity times radius, and that's conserved. It's constant in the absence of external influences. And so as you decrease the radius, you increase the sideways velocity so that angular momentum is conserved. At the end of the skater's routine, she pulls in her arms, she spins faster and faster and faster. Here in these images here, you can see if you've got a large radius, you'll have a small sideways velocity. If you have a smaller radius, you'll have a larger sideways velocity, so that the product of these things remains the same. And the skater, before she's pulled in her arms, is analogous to the core of that massive star before it's collapsed. And then once it has collapsed, any rotation that it had will be now larger than what it was before. You'll have a smaller object, the neutron star, and a much larger rotation rate. So, what can happen to a neutron star in a close binary system? Imagine that you have a neutron star in a binary and it's accreting matter from its companion. So the neutron star is at the center here of the accretion disk. That's what can happen. This is similar to what we were talking about earlier today with white dwarfs. Matter falls down onto, before the white dwarf, now the neutron star, and makes an accretion disk around it. Those accretion disks are, again, very hot. So you look for them in the X-rays. And in fact, around neutron stars, where everything is even more compact, they can get even hotter than before. And you can also have matter from the inside of that accretion disk fall down onto the neutron star, make it spin faster and faster and faster. And also you can have episodes of fusion on the surface of that neutron star that leads to X-ray bursts. So here we're looking at matter as it inspirals in. You can think of it as there being some friction, if you will, some viscosity, if you will, inside of that accretion disk, which causes it to inspiral rather than just to orbit indefinitely. And as it falls down in onto the neutron star, it can spin it up faster and faster and faster. So the fastest spinning neutron stars, so-called millisecond pulsars, these ones are spinning many hundreds, several hundreds of times per second, and they're often spun up, or recycled as it's called, by having accreted matter from a companion in this way. Here's a question for you. According to conservation of angular momentum, what would happen if matter orbiting in a direction opposite the neutron star's rotation fell onto that neutron star? A, the neutron star's rotation would speed up. B, the neutron star's rotation would slow down. Nothing. The directions would cancel each other out. Pause it if you like. So the idea here is that the neutron star would slow down because it's spinning one way, but then the matter falling in would tend to slow down that rotation because it's in the other direction. And so if you accreted enough mass that was falling in, and if the star wasn't rotating quickly to begin with, you might actually get it to stop and then start rotating the other way in the same direction that the material had fell in at. If I go back to this image before, imagine that this neutron star were rotating counterclockwise, and the material, as shown here, is falling in around it clockwise. Well, that counterclockwise rotation would be slowed down by the infalling clockwise material that was being accreted. So the answer here is B. I mentioned that there are X-ray bursts. Here are some example data of X-ray intensity on the vertical axis versus time on the horizontal axis during one of these bursts. So these fusion events where material that's accreted from the companion is fused on the surface of a neutron star are short-lived. You can see that they last for about a second. And there are different types of X-ray bursts, but this is an example of an X-ray burst and its observational data. Now we have a little bit more time today to move onward and upward and to talk about our last of the compact objects, the so-called black holes. And so we'll go ahead and do that now. A black hole is an object whose gravity is so powerful that, at least if it's close enough, nothing, not even light, can escape it. This term was coined by John Wheeler, and it's a pretty good name because if you think about it, if light can't escape, then it means that you wouldn't be able to see anything coming from it. It's going to look black as a result. As a footnote, there is something known as Hawking radiation, which is a quantum mechanical effect where you do have particles escaping from black holes. Those, though, are outside of the what we'll define soon to be event horizon of the black hole. So even if we think about Hawking radiation, which some of you might have known about and been wondering about, it's still the case that if you're close enough to a black hole, nothing can escape. So we're going to be able to characterize black holes purely by their mass and their spin and their charge. Black holes do not have hair, is the phrase that people often say. In other words, people, for example, they have different colored hair, and some's curly, some straight, some people are bald, etc., etc. Everybody is a little bit different in the hair they have. Black holes, you only need three quantities to characterize them. You say the mass, you say the spin, you say the charge. You've said everything that you can say about that black hole. All right, well, let's move on, and let's keep in mind as we go to the following slides this statement here, that because nothing can travel faster than light, that if you are in a region where light can't escape, nothing else is going to be able to escape. The way that you make a black hole is through a massive star supernova, but the star you start with has to be at least about 15 or so solar masses or more. If it's in the 8 solar mass to 15 solar mass range before it blows up, you're going to make a neutron star. But if it's more than about roughly 15 solar masses, then the core that you have that's collapsing down in on itself, triggering the massive star supernova, is actually going to be more than 3 solar masses, which is the most mass that can be supported in a neutron star. People argue about the exact upper limit on the mass of what a neutron star is. It's not as well known as what the maximum upper limit mass is for a white dwarf, but it's somewhere around 3 solar masses. And if your object is more than 3 solar masses, there is no pressure that can support it from collapsing. And so what will happen is the star will collapse down and form one of these black holes instead. As far as we know, according to the best laws of physics that we have so far, the black hole is a singularity, that the mass gets crunched down to a single point in space. So even though the black hole has a mass, it has 0 volume. And so it is a singularity, something that is infinitely dense. That makes black holes the most compact of all the compact objects. Let's, for example, consider 3 kinds of objects, all of which have the same mass as the sun. If you take a white dwarf is about 10 to the 9 or a billion kilograms per cubic meter. And so if you take one of those white dwarfs and imagine having a tablespoon, and somehow you could get that tablespoon of the white dwarf onto the surface of the Earth, it would weigh 10 tons, that tablespoon of the white dwarf. If you took a neutron star instead, it's a billion times more dense. So that neutron star would actually weigh 10 billion tons if you had a tablespoon of it on the surface of the Earth. And now if you take a black hole, well, we just got done saying that a black hole had 0 volume and a finite mass. So the black hole is really infinitely dense. In a moment, we're going to define what an event horizon is. It's going to be the boundary inside of which nothing can escape. And even though the mass of the black hole need not be spread out over the entire interior inside the event horizon, if we averaged the mass over that interior and calculated an average density, what we get is something even more dense than a neutron star, about 10 times more dense than that. So you can now really start to appreciate why these objects are called compact objects. They are very, very compact. They are very, very dense. Here I have a thought question for you. What happens to the escape velocity from the surface of an object if you shrink it? So to shrink means to decrease in size, but not in mass. And so the hint down at the bottom here is reminding you of what the gravitational force is between 2 objects. If you know the distance between their centers, that's what d is, and you know their masses, you can take the product of their masses over the distance squared. Okay, the answer to today's reading quiz question is: the Earth is an apple. The Earth is an apple. Hope you get it. I've got here an apple and a tangerine, and I'll let the apple represent the object before we've shrunk it, and the tangerine after. The apple's a little bit bigger than the tangerine. And so the idea is that you imagine something that's on the surface of the apple. The apple maybe represents the Earth before we've used our supernatural powers to shrink it. And I imagine shooting it off. If it's the Earth, I have to shoot it off at 11 kilometers per second for it to be able to escape and never fall back down. If we go at a speed less than 11 kilometers per second at launch, then it'll eventually slow down, stop, and get pulled back to the Earth. 11 kilometers per second is what we call the escape speed. It's the minimum speed we have to give it in one boost in order for it to escape. Now, if instead you're trying to escape from the Earth shrunk down, would you need to fire it at a speed that was more than 11 kilometers per second? If so, you would want to answer A here. Less than 11 kilometers per second? If so, you'd want to answer B here. Or the same as before, still the old escape speed of 11 kilometers per second. If so, you'd want to answer C here. Go ahead and pause it if you like. All right, so in this case where you're launching something at 11 kilometers per second, what's going to happen? it's going to slow down as it goes off. 11, 10, 9, 8, all the way until eventually it reaches infinitely far away where it approaches a speed of 0. Now, if you instead are launching it from a smaller object, still on its surface, you're going to want to keep in mind that you've got to cover that first little bit of distance that would get you out to the previous radius of the Earth. And then thereafter you could have the same kind of motion as before. So if you launch it at 11 kilometers per second, like let's say you think the answer is C, by the time you get out to the previous radius of the Earth, it'll be moving slower. Let's say it's moving 9 kilometers per second. And then thereafter, it would not be moving fast enough to escape, because when it gets to the previous radius of the Earth, it would have to be moving at 11 kilometers per second to be able to escape. And so the answer here is A. You need to fire it off at a faster speed if you're talking about a smaller object of the same mass. Let's say you fired it off at 13 kilometers per second, and then it goes to 12, and by the time it gets to the original radius of the Earth, it's 11 kilometers per second. And then thereafter, it would take the same kind of motion as before. And so what's really important here is that you, bye Bella, is that you take into account that it's really only the mass, it's the distance between the centers of the objects which matter, and it's the mass of the object that's pulling back on you that matters. All right, let's move onward. Here's a little interactive figure that may help us to understand this even better. Here we have the Earth. It has the size of the Earth. They're around 5,800, almost 6,000 kilometers. Around 6,000 kilometers. And imagine you could take that Earth and shrink it down. So you make it smaller and smaller and smaller. And as you do, the escape velocity gets bigger and bigger and bigger. When we started this, there's the escape velocity, about 11 and a half kilometers per second. You make the Earth smaller and smaller and smaller. Look at that escape velocity get bigger and bigger and bigger. At this point, it's 3% the speed of light. Make the Earth smaller still. Now it's 0.56% the speed of light. And we keep going. If you bring it down all the way to a size of 1 centimeter, the escape velocity becomes 94% the speed of light. And if you made it even a little smaller still, then the escape velocity would equal the speed of light. At that point, you would have shrunk the object down, made it dense enough that it would have become a black hole. Because if you've crushed it down to such a small size and the escape velocity is now the speed of light, even if you try to go outward, you won't go out, you'll go in, and you will be destined to be collapsed down onto the singularity of this black hole. Now, general relativity is our best theory of gravity. Right? When you hear the terms general relativity, you think of Einstein 100 years ago. It sounds like a complicated theory, and mathematically it is, but conceptually general relativity is actually fairly straightforward. It's nothing to be afraid of. You can think about general relativity in the following way, that mass will warp the space around it, and then objects move through that warped space and respond to its curvature. And so here, you can think about taking the three-dimensional spatial world that we live in, plus the one dimension of time, and suppressing one of those spatial dimensions so that you have just a flat sheet. And then you put down on that sheet a ball bearing, perhaps representing the sun, and that sheet gets curved as a result. And then other objects move in response to that curvature. So Mercury circulates around Venus, Mars, Earth, etc. and they're moving in response to the curvature. You no longer really need to think about gravity as a force that acts at a distance. Instead, you think about gravity as being the curvature of space, or more precisely in general relativity, space-time, because time is given the same kind of footing as space in the expressions of general relativity. Here we have a little interactive figure that allows us to play with this idea. This yellow circle here is representing the outer boundary of some object. In this case, the object is our sun. And the sun has so much mass, and so it warps the space around it. It's not just black holes that warp space. It's any kind of energy, mass included, that warps space. If I were thinking about a red giant instead, it would be larger in scope. If I were thinking about some compact object like a white dwarf, it would be smaller in scope. And if I went down to a black hole, that's the smallest of them all, and this really just kind of becomes a throat that opens up, with the slope of this sheet getting steeper and steeper as we get closer and closer to the black hole. I can also play with not just the size of the object, right, but I could play with the mass of the object as well. Right now I have the mass fixed, and I'm changing the size, and you can see that far away from the object, the curvature of the sheet is not changing at all because I'm not changing the mass. If I instead change the mass, then I change the curvature of the sheet everywhere. A really low mass object wouldn't indent the sheet significantly. You just have what we would call flat space. And objects would just move along on straight lines because there was no gravitational pull on them that would deviate their motion. If we have a very massive object, then the space around it is curved strongly. And as before, we can imagine these orbits that occur in the presence of masses. These orbits are called geodesics, or the trajectories that the objects take through space are called geodesics. A geodesic is the shortest path, if you will, between 2 points. And so in this context, what that means is that at every moment in its motion, the object is attempting to move straight. But because it is on a curved sheet, when viewed from afar, you see the curved motion when taken over this more global view. And so if you give an object just the right sideways velocity, it would tend to orbit around in a circular motion. If you give it a different sideways velocity than that, you could imagine having some kind of elliptical orbit. Or if you give it a different velocity still, say a larger sideways velocity when it's at its point of closest approach, then you could have an unbound orbit. So the circular, elliptical, parabolic, hyperbolic orbits that we talked about, they are all able to be explained in this new way of looking at gravity. Well, that's all that we have time for today. Stay in contact. I hope that you're all doing well. Stay safe and take care.